Okay, so in electricity, we're going to see three big ideas. We're going to see forces, electric fields, and electric potential. And I want you to know what each of these are and be able to apply them. Um, in addition, we'll also see potential energy, but potential energy is closely related to electric potential. In fact, they're all related. They're all related, and they all go back to this initial idea of force. So the first idea we'll see is force. Force is a force, as you know, we know what a force is. It's a push or a pull. When we have two or more charges, they exert forces on one another. If they're like charges, they're going to repel one another with a force. If they're opposite charges, they're going to attract one another with a force. A field is a force per unit charge. And for field, we're going to use the letter E for electric field. And it is a force per unit charge. Remember that, force per unit charge. And then potential, which we're going to use the letter V for reasons that I don't know why we use V. It's voltage is another word that we use for it, but potential is an energy per charge. And I'll write out energy so we keep it separated from, force. Energy per charge. Okay, force, field, and potential. Well, let's begin with force. We observe electric forces between two or more charges. Whenever we have two or more charges, we observe a force. Forces always require at least two bodies, and that's a really nice application of Newton's third law, that if I just have a single charge out in space, no other charges around it, it will not experience any forces. But if I have two charges, let's say that one is positive and one is negative, these are going to experience forces that are equal but opposite. Equal and opposite forces. And Coulomb's law describes this force. We give Coulomb's law as K, Q1, Q2, divided by D squared, where Q1 and Q2 are just the charges, how much charge do they have, and then also D is the distance separating them. K here is a constant, it's Coulomb's constant. Doesn't really matter what it is, it's a really big number. You're not going to have to calculate the force, but of course you will need to know this equation and know how to apply it. That if I change, say for example, the distance, what's going to happen to the force? Well, here D is the distance between them. For example, if I double this distance, then I'm going to quarter the force. If I triple one of these charges, then I'm going to triple the force. So of course you'll have some questions that'll be similar to something like that, where I give you changes in those values Q and D and ask you what happens to the force. So the like charges repel. So if I have two positive charges, they're going to be opposed to one another. Opposite charges attract. You probably know this. You probably did this in high school. Opposite charges will attract like that. If you have multiple charges, you will have multiple forces. Let's draw the forces that are acting on Q3. So if I draw these forces, I'll have one attractive force due to particle 1. I'll call that F1. I have another repulsive force due to particle 2. I'll call that F2. And then I have another attractive force due to particle 4. I'll call that F4. And as we did before, I can draw a net vector. Let's imagine a simpler diagram. Say I have them like this. Let's say that they're all positive, and I want to know what is the net force acting on this particle. I'll have one repulsive and another repulsive, and so the net force that's acting on this particle is going to be in this direction, because those two vectors will add to give a vector that's in between the two. In your book they do this, but we can calculate the electric force just to give you some sense of reference between two carbon atoms that are separated by a distance of 0.5 nanometers. Carbon has a charge of plus 6e. That means that it has a charge of 6 times 1.6, which is 9.6 times 10 to the minus 19. coulombs. That's the charge of a carbon atom. And they are separated by that distance of 0.5 times 10 to the minus 19. Excuse me, 10 to the minus 9. That's nano right here. Meters. And then if I calculate F, which is KQQ over R, KQQ over D squared, using here for Q both times, this is for my distance D, then I get a force of 3.3 times 10 to the minus 8. I'll just show you this just to give you some sense of reference. You know what a Newton is. A Newton is about a quarter pound. This is the force between two carbon atoms that are really close to one another, a half a nanometer. A mass of a carbon nucleus is about 2 times 10 to the minus 26 kilograms. Oops, excuse me. So I can calculate the force, or I can calculate the acceleration then that this force produces. I know from Newton's second law that A is equal to F over m. If A is equal to F over m, that means that my acceleration is 3.3 times 10 to the minus 8 divided by that mass, 2 times 10 to the minus 26 kilograms, and it gives me, even though it seems like a really small force, it gives me a very large acceleration, or 10 to the 18th meters per second squared. That's a 1 with 18 zeros behind it. The body uses electric forces to move cations and anions around. Remember, cations are positively charged, and anions are negatively charged. Positive, negative. So if I imagine these two particles, I have one positive and one negative particle. I want to know what direction will these particles move. Well, I have positive charges over here and negative charges over here. So this positive particle is going to be attracted to the negative particles and repelled from the positive particles. The negative charge is repelled from these negative charges and attracted to these, so it's going to move in this direction. Let me go ahead and introduce a different idea that I can talk about this in terms of just the charges that they feel. Later in the next section, we'll also begin to describe the field. So the field line here will run from positive to negative charges, and we'll find that positive particles will move along the field line, and we see that here, that this positive particle is moving in the same direction as the electric field. Remember, the electric field is a measure of force per charge. We'll see this again soon, so I'm just trying to introduce this idea right now. And then also, we will later define this as our high potential side, and this as our low potential side. The positive side is the high potential, and the negative side is the low potential. You can think about this. Remember, potential is energy per charge. So it describes how much energy a particle has as a divided by the total amount of charge. A positive particle will move from high potential to low potential. Positive particles sort of do what you imagine they would do. So imagine I have a mountain up here. This is the high potential. This is where it has lots of energy. And this is the low potential, where it doesn't have much energy at all. A positive particle will always move from high to low potential. Likewise, in living cells, charges will move, if they have a positive charge, from high to low potential. Negatively charged objects sort of do the opposite of what you would think. And in this case, this negative particle moves from our low potential to our high potential. And if I think about my mountain, that would be like my negatively charged stone, if you will, or ball, moving uphill, that it moves from low potential to high potential. All right, we'll see more of that in the coming sections. I just want to introduce those ideas.